Okay, thanks. So norm and trace of the metric tensor. ये तो समझ में आ गया ना, यहाँ तक ये वाला पार्ट सबको.
Yes, sir.
ठीक. So G alpha beta square, G alpha beta, G alpha beta. So it will be canonical delta, alpha alpha. So see, in D dimension, it is written as capital D. Okay. So it is a norm. Okay. Similarly, the trace. Trace is this. G alpha alpha is a trace. It is again D in D dimension. Okay. So consider a rank 2 tensor for special relativity purpose. Consider a rank 2 tensor. So T alpha beta is a rank 2 tensor. Is a covariant. You want to convert it into the contravariant. In special relativity, see, ये ध्यान रखो ध्यान से. अल्फा लिखो या कुछ भी इंडिसेस लिख दो. म्यू, बीटा यहाँ लिख दो न्यू. Now you can raise the indices mu, nu. Okay, it is in the general relativity. In special relativity, instead of G, you should write down eta. Okay, so in this way, you can contract, you can raise or you can convert covariant tensor into the contravariant tensor. What is the equation number? 28, 29, 30, 31, 32, 33. Okay. Now let's discuss about the anti-symmetry of the tensors. For 33 and it is 34. Next heading is the anti-symmetry of the tensor. Okay. See, anti-symmetry of tensors are defined only for the rank 2 tensor or higher than rank 2 tensor. Below rank 2 tensor, you cannot define the anti-symmetry. Okay. And for the contravariant or covariant properties for the tensor. Okay. So suppose rank 2 tensor is T alpha beta, covariant form, or T capital alpha beta, capital T alpha beta. It is a contravariant, rank 2 tensor. So what is the symmetry part? Symmetry is this. T alpha beta is T beta alpha. So it is a symmetric. Antisymmetric, T alpha beta is equal to minus T beta alpha. Okay, 34. Okay. So it is the antisymmetry property of rank 2 tensor. Now let's discuss rank 3 tensor, either covariant or contravariant. Rank 3 tensor means alpha, beta, gamma, either this or alpha, beta, gamma. Okay, so let's choose the covariant tensor. So first discuss the symmetry part. Symmetry, partial symmetry, individual. T alpha, beta, gamma will be symmetric to T beta, alpha, gamma. Okay, so this tensor is symmetric after the exchange of first two indices, alpha, beta and beta, alpha. So there is no difference. It is symmetric. And next one is alpha, beta, gamma is. It is also symmetric in the last two indices. Okay. Now which one is left? It is symmetric in first two indices. It is symmetric in the last two indices. And which is left? So the third one is the exchange of first and the third indices. It is also symmetric. So it is 34, 35. So it is a symmetric third rank tensor. Okay. It is a partial symmetric, and the fully complete symmetric tensor is this. Alpha beta gamma is equal to T, beta gamma alpha is equal to T, gamma alpha beta. Okay. This is a fully symmetric tensor. Okay, now let's discuss about the anti-symmetry. यहाँ तक ठीक है ना? ये समझ में आ रहा है ना? ऐसा तो नहीं मैं बोल रहा हूँ सुनाई नहीं दे रहा हूँ. ठीक है. ठीक है, समझ में आ रही है बात? ये नहीं?
यस सर.
ओके. और ये मतलब ये ऐसा ही है, ये मैथमेटिकल है ना. मुझे मालूम है इसमें थोड़ी प्रॉब्लम होती है सभी को, बट कुछ कर नहीं सकते ना. इवन आइंस्टीन को प्रॉब्लम फेस करना पड़ा था, तो हम लोग क्या है. आइंस्टीन लगभग 10 साल तक ऐसा मैथमेटिक्स ढूंढ रहे थे जो उनकी थ्योरी को एक्सप्लेन कर सके, मतलब मैथमेटिकली. तब बाद में उन्हें अपने एक फ्रेंड की हेल्प से ये पता चला कि टेंसर एनालिसिस जो है वो इनकी थ्योरी को मैथमेटिकली सही से एक्सप्लेन कर सकता है. ठीक है, तो ये है ऐसा. है ना. मैं ऐसा ही हूँ, ये कह रहा है मैं ऐसा ही हूँ, तुम मुझे जैसा भी ट्रीट कर लो, लेकिन मैं ऐसा ही हूँ. तो इट्स अबाउट द सिमेट्रिक टेंसर. लेट्स डिस्कस द एंटी सिमेट्रिक पार्ट. एंटी सिमेट्रिक. First, discuss the partial antisymmetry. So, in the previous case, third rank tensor was symmetric in the interchange of first two indices. Now, it is not symmetric. So, there is a minus sign when you interchange first two indices. alpha beta, beta alpha. Similarly, it is not symmetric in the interchange of last two indices. Similarly, it's not symmetric in the interchange of first and third indices. Okay. It is the partial antisymmetric condition. And what is the complete antisymmetric? T alpha beta gamma is equal to T beta alpha gamma is equal to T gamma alpha beta, but equal to minus T beta alpha gamma minus T alpha gamma beta minus T gamma beta alpha. Okay, similarly, antisymmetry can be defined for higher rank tensor. Okay, you can define a similar way any tensor which is higher than 2 rank, mean third rank or fourth rank tensor. Okay, is it okay?
Sir,
हाँ बोलो बोलो बोलो.
sir, the second term is you repeated again. I think you written wrong.
Oh, let me check. T alpha beta gamma is T
T
beta.
beta
Oh,
alpha
oh,
gamma
okay.
repeat.
Oh, beta gamma alpha. Yes. Thanks. Thanks. Now it's fine, na?
Yes, sir.
Yes, fine. It's good. You point out. Very good. Okay, so in this way, you can write down these things. So I will discuss a few tensor related things, but not in the today class. Okay, because I know very well that you will be bored with this lots of the tensor calculation. Okay, so but I need to introduce one more thing related to the tensor analysis. This is the tensor calculus, because we only discuss tensor algebra. What is the tensor? What is the type of the tensor? How we can add to tensor? How we can multiply one tensor to another tensor? And what are the properties of the symmetric and antisymmetric of the tensor? But we don't know how we can differentiate, okay, or how differentiation is used in the tensor analysis. So this is known as the tensor calculus. तो मैं शॉर्ट में ही बता रहा हूं अभी. So first is the differentiation. So in tensor calculus, differential operator is this. Del mu is a differential operator. It is written as del x mu. And really it is del upon del x 0, del upon del x I, or in short form del 0, del I. Okay. And what is del x 0? It is 1 upon C del over del t. It is Laplacian operator. Okay, so it is equation 37, 38, 39. Okay. So similarly, there's another differential operator, del mu. So which is eta mu alpha del alpha, which is eta mu alpha. Oh, sorry. Mu alpha del over del x alpha, which is del over del x mu, which is del mu actually. Okay. Is it okay?
Yes, sir.
So this is, and this del mu, which is actually del over del x mu, which is written as del over del x 0 del over del x I. So see, del over del x 0 is similar to the upper one. So it is del not, but the another one is the minus. Okay, in this case there will be one minus sign. Please keep in mind why it's coming. It's just coming due to the metric structure, because in the metric time part is positive and the space part is negative. That's why there is a negative part. 41. Okay, so please memorize this or keep in mind. Otherwise, life will be very difficult to you. Okay, so we can define gradient divergence of curl in the tensor notation. I hope everyone is familiar with the gradient divergence and curl. Is there anyone who is not familiar with the gradient divergence and curl? Okay. See, suppose there is a scalar phi and you are differentiating del mu phi or okay. So it is known as a gradient. Okay. Okay, it is a gradient. It is a definition of the gradient. 41, 42. Similarly, divergence is this. Okay. And it is a divergence of a vector. Similarly, divergence of a tensor. Okay. You can contract alpha also. And similarly, there is a definition of the curl. Okay. Curl is this, a vector of maybe A alpha or any tensor. The curl of this E alpha beta mu nu del mu A nu. Okay, so it is equation 43. Okay. I will explain more about this, about curl. Okay, when it comes to the picture, then I will discuss. Dear Lambershi. Okay, and it is nothing but del 0 del I, which is 1 by c square del square del t square minus del square. Okay, it is a D'Alembert operator. So it's all about the tensors. Okay, so maybe in the next class I will start general relativity, or maybe after the few discussion of the special relativity I will move towards general relativity. So there is no more mathematics. I will use this mathematics. Okay, there is a little bit mathematics, and remaining part, the philosophy, the theory, I will discuss. Is it okay till now? So then you can stop the recording, I think.
Okay, sir.